Okay, welcome to the NUPOC video study guide number 59. So let's take a look at another question that uses implicit differentiation and kind of gets us into some of the related rate problems that we've been talking about. So let's consider this question where it asks us to consider fluid flowing in a pipe with a certain velocity that's dependent on the distance from the center of the pipe according to this equation here, where this is the magnitude of the velocity, right? The magnitude of the fluid flow velocity, and it's equal to some constant c times, this is the outer radius of the pipe squared, minus the radius at which the flow is occurring squared. So if we were to draw that out, for example, if we were to draw the cross-section of the pipe, it would look something like this. Here's the center of the pipe, and there's capital R, the outer radius of the pipe, and maybe we're talking about fluid flowing some distance, little r, right? And that fluid will have a certain velocity, and let's call this little r1, and then maybe at another distance from the center, right, we'll call this little r2, the fluid would have a different velocity flowing through the pipe. And in fact, it would be slower because if we look at this expression here, we can see that if r equals 0, little r equals 0, that means that's the fluid flow at exactly the center of the pipe. The velocity is c r squared, c big R squared, that is. And if little r is all the way out at the perimeter, then it's simply equal to uppercase R, and so this term here is going to be 0 because it will be big R squared minus big R squared. And so what we see is that the fluid flow will be 0, the velocity will be 0 at the perimeter, and a maximum at the center of the pipe. So if we were to look at this, sort of taking a cross-section kind of through the side of the pipe instead of cutting the pipe on end, what we would see is the fluid flow, right? I think you can kind of draw it like this, right? Right, so we've kind of cut the pipe in half lengthwise. So the fluid flow will have maximum velocity down the center of the pipe, right? And this distance here, this is r, and this is, v, right? And maybe at some distance, this is maybe r1, there's some velocity, right? We'll call this v naught, or we should call it v max actually. And this is maybe v1, and then maybe some slightly bigger distance from the center of the pipe, r2, will have a slightly smaller magnitude of the velocity, right? So that's kind of what we're looking at here. That's what the problem sets up for us. So now it asks us, if the pipe expands at a constant rate, how does the velocity of the fluid change with respect to time at any lowercase r? So what they're saying is, if this pipe were to start getting bigger at a constant rate with respect to time, or in this figure, these walls start moving apart here, right? And it starts expanding. So big R starts increasing. The pipe is getting bigger, right? What happens to the fluid flow? Because we can see here that it is dependent on big R squared. So in fact, if we just looked at the velocity, the maximum velocity at the center of the pipe, okay, where little r is 0, okay, the maximum velocity is c r squared. So as the pipe expands, okay, as big R starts increasing, the maximum velocity of the fluid has to go up. And in fact, the velocity all the way out to the perimeter will go up, because now the little r that used to be at the perimeter, as r expands, that's no longer at the perimeter. So it now, instead of being 0 velocity, has some velocity to it. And so at every r in the pipe, as the pipe expands, the velocity of the fluid flow at that little r will increase. And so the question is asking, at what rate will the velocity increase with respect to time if the pipe is expanding at a constant rate with respect to time? Okay, so we're sort of given, well, we don't know exactly what it is as like a number, but we're given that we would know the rate of change of r, big R, with respect to time. That's the rate at which the pipe is expanding, the rate at which R, big R, is increasing. So we this is sort of assumed to be known, okay? And what we don't know is, or what we want to find, is the change in velocity, fluid velocity, with respect to time, okay? So we don't know that, okay? So how are we going to do this? All right, well, let's just go ahead, and we know what V is here. We know it's this equation. So let's just apply the differential operator to both sides of this equation up here, right? So we would get dv dt, right? That's the left side, equals, we'll just pull the c out because that's a constant, right? And we can just apply the differential operator to each of these terms, right? So we would have d dt of, well, I'll just write it up here, dr squared, big R squared dt minus d little r squared dt. Okay, and here's where the implicit differentiation comes in, because big R, right, we know that it's changing with time, but we don't know exactly what the function is. We just know that it's something, right? Well, I guess we do know that the problem does say it's a constant rate, but even if we didn't assume that, we know that R is a function of time, but we don't know exactly what it is, so we have to use implicit differentiation. So, you know, you might be tempted to say, oh, you know, dr squared dt, that's just 2r, right? But it's not, because we don't know exactly what the function r is in terms of time. Is it t squared? Is it 1 minus t? Is it t plus t squared plus 1? I mean, we don't know, so we have to use implicit differentiation. So let's go ahead and solve this. And we know r, any particular r, isn't changing with time, so this we could just call 0. But let's do that out using implicit differentiation, just to make sure we're doing everything thoroughly, right? So this is going to be equal to c, and then this first one here, we'll do our implicit differentiation, which is just the chain rule, remember? So we will have, taking the chain rule, we'll have dr squared dr, okay, we know what that is, that's 2r, okay, times dr dt. And we don't really, we assume we know what it is. We don't know exactly what it is, right? But we just assume it's something that's known, okay? Minus d little r squared dr times dr dt, okay? And we know dr dt is 0 because each individual r in the pipe is not changing with time. So this whole term is going to be 0. And so we know again that this is 2r, so what we have is dv dt equals 2rc, and then we have this dr dt, right? So that's essentially our answer, right? So we use implicit differentiation to solve this related rate problem, right? So what we know is the rate at which the pipe is expanding. I mean, we don't know exactly what the function is, but we assume it's some known, right? We assume we have it, and we use this rate, this known rate, to find out what this other rate is, the change in fluid flow velocity with respect to time at any r. So it doesn't matter whether r is right at the center or halfway out. As the pipe expands, this whole 2rc dr dt is how the velocity of the fluid at any r in the pipe is going to change. Now, something interesting. If you also wanted to find, for example, not how the fluid flow changes with respect to time, but with respect to r, right? So if we wanted to find dv dr, right, we could just rearrange this algebraically. We bring this dt up here, bring dr down here, and we'd find dv dr equals 2rc, right? And another way you could kind of intuitively know that is because if you looked at this factor here, right, and you looked at, well, we have dv dt over here, and we have dr dt over here, what factor in the middle would we need to make dr dt equal to dv dt, right? have dv dt equals something times dr dt. Well, we'd have to cancel out this dr, so there'd have to be a dr on the bottom, and we have to add in a dv, so there would be a dv on the top, right? So look at that. So it looks like 2rc is the same as dv/dr, which is what we have over here as well. So anyways, some problems, when you get into related rates, ask you this type of thing. They don't ask you how does the velocity change with respect to time, knowing that the pipe expands. It may say, the pipe is expanding, now how does the velocity change with respect to that changing radius, or with respect to that expansion? So if the problem were to ask you that, this is what you would find for the solution. And this is a really great calculus application to engineering. It's very relevant, fluid flow in pipes, very relevant to engineering, fluids, mechanical engineering, and all of those things. And if you want another practice problem with this, the problem that this is based on, if you use that link that I gave, I think it was 2 videos ago, to the problem sets for a calculus text, it has the worked solutions there to odd-numbered problems. If you look for problem 105 in section 2.4, you'll find a similar problem. This problem is essentially based on it. There they use blood flow in an artery, but it's very similar. And in fact, in that problem, they give you a numerical. They give you sort of a constant for what dr dt is. They give you what the constant c is, and all of these things. So you can solve it numerically and say, okay, what is dv dt numerically given what dr dt is, and some of those things. So if you want to work through a numerical example, that's where you'll find it. And so we'll go into some more related rate problems after this, but I think this is a good introductory problem where we just straight up use the implicit differentiation, do our related rates and all that, and it has some great. It's very relevant. It's a great application of calculus to some of the engineering that mechanical engineers, maybe nuclear engineers, do on probably an everyday basis.